part 3 of this course. We will primarily discuss about semiconductor light sources, structure, device structure, principle of operation, characteristics and output characteristics. These will be mainly covered in this part of the course. So, we start with the injection electroluminescence. Injection electroluminescence. So, electroluminescence refers to luminescence in the presence of an electric field. Luminescence, that is generation of light in the presence of an electric field. And injection electroluminescence refers to generation of light in the presence of an injection current. This injection refers to injection current. So, generation of light in the presence of an injection current is injection electroluminescence. We are primarily concerned with injection currents in a forward biased p-n junction. In the junction area, we are interested in the junction area or active region, because we will have, when you forward bias, we will have quasi Fermi levels, and the difference separation between the quasi Fermi levels can be controlled by the forward bias, and this will determine, or this will enhance the emission efficiency, or the, if you recall, the rate of spontaneous emission. We had an expression for rate of spontaneous emission. This expression, whatever expression that you had, will get multiplied by e to the power EFC minus EFV by kT if you forward bias the junction, where EFC minus EFV will be the separation between the quasi Fermi levels. So, by choosing appropriate separation here, you can change the rate of spontaneous emission, which is nothing but the number of emissions per unit time per unit volume from the material can be increased by orders of magnitude, and so that you can have significant emission of light. So, we are interested primarily in injection electroluminescence. Let us recall some amount of, because we are now discussing generation of light, and light generation comes from the recombination of electrons and holes in a semiconductor. So, let us first start with a discussion, a brief discussion on the rate of generation and recombination of carriers in a semiconductor. Rate of generation and recombination. If you consider a semiconductor at thermal equilibrium, so we are looking at thermal equilibrium. Let N0 and P0 be the carrier concentration in this piece of semiconductor. This is a semiconductor. N0 and P0 are the steady state carrier concentrations in this semiconductor. This semiconductor may be p doped or n doped, or as in the case of the junction, it could be p and n. So, N0 here refers to Ni plus Nd if it is n doped, where n is the donor concentration, intrinsic plus donor concentration, and P0 is Pi, which is equal to Ni, intrinsic concentration plus the acceptor ion concentration. So, N0 and P0 are the carrier concentrations in thermal equilibrium. Then the rate of generation, if I want to call it as G0, rate of generation is proportional to N0 into P0, and rate of recombination R0 is the same as rate of generation. So, this is N0 and P0 Please see, N0 and P0 are the carriers available in the semiconductor. In a semiconductor, as we discussed earlier, there is continuously carriers are generated because of thermal energy. Carriers continuously make upward transition, but also they make downward transition, which means electrons keep recombining with holes. But at steady state, there is N0 is the number of carriers here, the concentration of carriers, and P0 is the concentration of holes. Therefore, the rate of this is generation of carriers, absorption of energy or maybe thermal energy, because we are in thermal equilibrium, that generation, rate of generation and rate of recombination. The rate of recombination is proportional to N0 and P0, which we can write as a proportionality constant, rate constant R into N0 P0. Since it is in thermal equilibrium, rate of recombination must be equal to rate of generation. Therefore, R0 equal to R into this must be equal to G0. Rate of recombination, R0 is rate of recombination, is proportional to this R is a rate constant, this is a rate constant. Proportionality constant, which depends on the property of the material, depends on the material. When I say material, it will depend on whether it is a direct band gap material or indirect band gap material. It will also depend on the defect density in the material, traps and defects in the material. So, it depends on the material, the rate constant. So, R0, rate of generation, equal to rate of recombination. Assume that now we put a beam of light separate from outside, which creates additional electrons and holes. That is, we are now moving to quasi equilibrium. So, somehow if we create additional electrons or holes, or if R is the rate of injection, that is generation of carriers, additional, not thermal, additional rate of injection or generation of carriers. Why do I use the word injection? Because normally we have this additional carriers injected through a forward biased p-n junction. That is why we use the word injection. So, you take a p-n junction and forward bias this p-n, then as we have seen this carrier concentrations and how the profile changes. So, if you plot the p and n concentration, so this is p side and this is n side. So, p concentration varies like this and drops down as you go across the junction, and this is the electron concentration. So, this is n and this is p, carrier concentration. If you inject, if you forward bias the diode, then there will be more carriers injected into the junction region here. So, this is with forward bias, this is with forward bias, and similarly there will be more electrons injected into the junction region. So, if you look at the junction region, you recall again from the various pictures, whichever picture is convenient to you, you can look at that. So, this is the band diagram, energy band diagram of the p-n structure before forward biasing. Once you forward bias, this raises up, this also comes up. So, let me differentiate this part to show that this is the forward biased region. And then we have earlier electrons were up to this, now electrons have come up to this here, they have moved to this side, you can see here, and earlier originally holes were up to this. Now, because this band has moved forward, holes have come up to this, which means the junction region here where we have excess carrier concentration, excess of electrons and holes, excess because of the injection. And therefore, if I look at the junction region, then if R is the rate of injection, which means if delta N and delta P, so delta N equal to delta P is the rate of delta N equal to delta P is the rate of carrier injection, that is excess carrier concentration, excess carrier concentration, excess carrier concentration. This is quite simple, that is why I am just speeding up, because we have covered all of these basics earlier. Then I have N is equal to N0 plus delta N and P is equal to P0 plus delta P. Delta P is equal to delta N. If you think of light generating, then also for every electron generated here, one hole will be left behind. Similarly, when you inject current, for every electron which is coming from the negative side here, a hole will be released here. Therefore, delta N is equal to delta P always, whether it is by illumination or by current. Therefore, N is equal to N0 plus delta N, P is equal to P0 plus delta P. And therefore, we now have rate of generation G0 plus R. This is R is the rate of injection. Please see, rate of generation due to thermal energy was G0. R is the rate of injection of carriers. Therefore, G0 plus R, this is proportional to N into P, or this is equal to the rate constant into N into P. What is N? N is N0 plus delta N, excess carrier concentration. P is P0 plus delta P. Therefore, this is equal to R into N0 plus delta N plus into P plus delta P, P0 plus delta P. That is equal to R into N0, so N0 P0, just multiply this P0 plus R into N0 plus P0 plus delta N into delta N. Delta N is equal to delta P. So, simply multiply 4 terms N0 P0, N0 delta P, and delta N P0 and delta N into delta P. So, I have taken one delta N here outside, recalling that delta N is equal to delta P, delta N equal to delta P. What is the first term? Rn0 P0. Rn0 P0 is nothing but G0. Therefore, G0 plus R is equal to this, or R, the rate of injection is related to this, so R into N0 plus P0 plus delta N into delta N. What is the unit of delta N? Carrier concentration. This is concentration, means the unit here is per cc or meter cube. This is also per cc, this whole term in the bracket. Rate of injection is number of carriers injected per unit time per unit volume. So, this is number per cc per second, the rate of injection here. Therefore, what is the unit of R? So, 1 cc cancels with 1 cc. So, R will have rate of injection so this is per cc, this is per cc. Therefore, the rate constant R here is unit of cc per second, cc per second. This R is equal to this, I write as delta n into tau, delta n into tau, where this whole thing, so this is the unit of R and this is the unit of cc. Therefore, this whole quantity has unit of per second. Please see, this quantity is unit of per second, and therefore, this write this as delta n by tau, because this is per second. So, denominator there is tau, no confusions. R is equal to this. I am writing this expression as delta n by tau, where tau is equal to 1 divided by R into n0 plus p0 plus delta n. If I call this quantity as 1 by tau, it is delta n by tau. But I wrote all these units just to say that yes, indeed this has units of inverse time. Therefore, it can be represented as some 1 by tau. This tau, so R is equal to delta n by tau. This is an important expression. This tau is called the excess carrier recombination time. Excess carrier recombination time. If the injection rate delta n is relatively small, injection rate R is relatively small, so that delta n, if delta n is much less than n0 and p0, then this can be written as tau is approximately equal to 1 divided by R into n0 plus p0. R is a material parameter. Why we are interested in bringing tau is because time is a measurable parameter. That is, lifetime of carriers is a measurable parameter. Experimentally you can measure. This was just a rate constant, proportionality constant, but tau is a recombination time which is a measurable parameter. Before I proceed further, this is approximately equal to, but as you will appreciate that if delta n is very large, then the lifetime here, excess carrier recombination time tau, will depend on delta n. When delta n becomes large in the denominator here, then it can no more be neglected with respect to these, and then you will indeed see that tau is also a function of delta n. The recombination time will depend on the injection carrier rate for higher injection rates. For moderate or low injection rates, when delta n is much less compared to n0 and p0, it is almost independent, and you talk of a carrier recombination time delta tau, recombination time tau in a given material, because it depends only on the material, its carrier concentration, equilibrium carrier concentrations, and the rate constant tau. Now, R is a rate constant for recombination. It is a rate constant of recombination. There are two types of recombinations possible. we have seen that transitions, an electron making a downward transition in and making a recombination, a electron and hole recombination here, may lead to emission of a photon. In this case, the transition is called radiative transition. So, radiative transition, radiative recombination. Or the electron may make a recombination without the emission of any photon, and in that case it is called non-radiative recombination. Non-radiative recombination. So, the recombinations have a radiative part and a non-radiative part. Accordingly, the total recombinations therefore will have a radiative part and non-radiative part, and we have R is equal to RR plus RNR. Recombination R, please see this, recombination R is proportional to R into N into P. Generation or recombination is proportional to, if the recombinations comprise of radiative and non-radiative, then I will have to write this as RR into NP plus RNR into NP. So, this is the meaning when I write like this, that the rate constant will comprise of a radiative part and a non-radiative part. So, do not use R here, you can write recombinations, because R I have used specifically for injection rate. So, recombination. So, recombination rate. So, recombination rate is proportional to N and P. Recombination rate is proportional to the number of electrons and number of holes, that is why it is proportional to the product, and proportionality constant is R. The recombinations comprise of a radiative part and a non-radiative part, and if I call RR as the radiative rate constant and RNR as the non-radiative rate constant, then I can write like this. Okay. Now, from here you can see that tau is inversely proportional to 1 by R, or R is inversely proportional to 1 by tau. Therefore, I can define a lifetime or a recombination time tau R, which is proportional to 1 over RR, and a tau NR which is proportional to 1 over RNR. Please see this. It will all become clear when we reach the required result. Right now, what we know is recombinations comprise of a radiative part and a non-radiative part. Accordingly, I have split R into RR plus RNR, and also since the rate constant is inversely proportional to a time constant, therefore, we define a radiative recombination lifetime tau R and a non-radiative recombination time tau NR. They may be very different, and so this is what I have defined. Why we have defined, it will become clear. Now, before I proceed, let me again give you an idea about this lifetime. I am sure many of you know this, and some of you have measured also minority carrier lifetime in semiconductors and so on. So, what is this lifetime? What it means is, lifetime at t is equal to 0. So, this is at t is equal to 0. If you inject a certain carrier concentration delta n0 here, delta n0, that is, you have a material. In this, let us say a burst of light has created delta n0 and delta p0, then it is only instantaneous, it is like an impulse. It has created delta n0 and delta p0. Then with time, because of recombination, this continuously drops down like this. The excess carriers go on reducing because they are recombining. If they recombine faster, then this rate will fall faster. If they recombine slowly, then this will go very slowly. And the tau that you have, you can find this from this expression delta n by tau. So, this is nothing but d by dt of delta n, which is a function of time. This is delta n 0, but what we are plotting is delta n with the time, how the excess carrier concentration is changing with the time in the material. So, this is, and where it falls to 1 by E. So, this is 1 by E of delta n, because if you differentiate this, then d of delta n, bring delta n here and integrate, then you will get this as dropping as e to the power minus t by tau. So, the rate at which it will drop. So, you will get a function here delta n of t is equal to delta n 0 into e to the power minus t by tau. And what is the tau? So, 1 by e of delta n 0, if you draw this line, then you will get this is tau. So, tau 1. So, this is case 1, case 2, case 3. This is tau 2. Just to recall the picture, that what is the picture of this time constant, recombination lifetime. What it means is, if tau is very small, which means the recombination rate is very fast, they are recombining very fast, therefore, the lifetime is very small. If tau is very large, it means the recombination rate is very slow, it is a slow recombination rate. This is important because now we have defined a radiative recombination lifetime and a non-radiative recombination lifetime. In certain materials, these two are indeed of the same order, and in certain materials they are highly different, very different, and you will see that the radiative lifetime is very large, but non-radiative lifetime is very small. For example, if a particular material has variation like this, that the delta n, the radiative time is very large. So, this is tau r, and the non-radiative time is very small. So, this is tau n r. Do not worry how we will differentiate between this is non-radiative n r, this is radiative drop, radiative recombination. Here I have plotted the total recombination. So, it is referring to tau. Here how I have done, do not worry about it right now, that I am looking at only non-radiative recombinations and only radiative recombinations. Radiative recombinations are very slow, non-radiative are very fast. But whether it is radiative or non-radiative, one electron and one hole is lost, the carriers are lost in recombination. Therefore, in a particular material, if non-radiative lifetime is very short, which means the carriers combine very quickly, mostly by non-radiative, therefore, within this time very few radiative transitions have taken place. Most carriers are already lost by non-radiative transitions, and therefore, the contribution to radiative transitions will be very little in the case of a material which has a very small tau nr. You will appreciate this now. If I write the typical example, let us take silicon, gallium arsenide, and if you want gallium nitride, what is tau r and what is tau nr? Typical material, okay? It will depend on defect density and carrier concentration and so on. Okay? A material where let us say N0 P0 is of the order of 10 to the power of 17 per cc. In silicon, the radiative recombination is of the order of 10 milliseconds. non-radiative is of the order of 100 nanosecond. In gallium arsenide, this is of the order of 100 nanosecond, this is of the order of 100 nanosecond. If you go to gallium nitride, this is of the order of one second, for gallium arsenide it is approximately tau r is 10 nanosecond, and this is 10 to the power of minus 1 or 0.1 nanosecond. Let me see if I have the values. For gallium nitride, tau r is 10 nanosecond and this is 0.1 nanosecond. That is okay. Tau nr. You see, for gallium arsenide, both radiative and non-radiative are equally probable. The time is the same. Recombination time is the same, which means the rate at which recombination is taking place is the same. If you take silicon, the rate for radiative is much larger, 10 millisecond. This is 100 nanosecond. So, the non-radiative lifetime is much smaller here, which means if I have 1 million recombination taking place, primarily most of them will be by non-radiative and very few will be radiative. Do you follow the importance of the lifetime? One is non-radiative, another is radiative. Whichever lifetime is short, which means that is the reaction which takes place very fast, or that is the recombination which is taking, because small lifetime means large rate constant, they are inverse. So, the rate constant is very large for that. Now, why did I discuss all of this? It is very simple, that we are interested in a parameter which is most important, called internal quantum efficiency. Internal quantum efficiency. In all semiconductor sources, this is the most important parameter which determines the efficiency of generation of light. Efficiency of generation of light. What is internal quantum efficiency? It is very simple definition. It is out of the total recombination, it is the ratio of radiative recombinations to the total recombinations. So, eta I is equal to ratio of radiative recombinations if you want, you can write per unit time, that is per second, divided by total recombinations, per second. This means, okay, let me erase this. If time permits, we will discuss a technique to measure the lifetime, but let us right now continue. That means eta I is equal to RR divided by RR plus R NR. You agree? Because radiative recombinations were RR into N into P, non-radiative recombinations were RNR into N into P. Therefore, total is RR N into P plus RNR N into P. So, NP is common in all the places, therefore, this is the ratio. But we have something here, R, this is the total. This is equal to RR is inversely proportional to tau R, which means 1 divided by tau R divided by 1 over tau R plus 1 over tau NR, because the proportionality constant is the same for a given material. What is 1 over tau R plus 1 over tau NR? Is 1 over tau is equal to 1 over tau R plus 1 over tau nr. Why? R is equal to RR plus this, therefore, this is inversely proportional. So, 1 over tau R is equal to 1 over tau R plus 1 over tau nr. 1 over tau equal to 1 over tau R plus 1 over tau nr. That is what I have written. The denominator is nothing but 1 over tau. So, this is equal to tau divided by tau R. Eta I is equal to tau divided by tau R. What does this mean? What have I written here? If there are, this tells us if there are 100 recombinations taking place, if 10 of them lead to the generation of photon and 90 of them do not lead to the generation of photon, then this ratio is 10 divided by 100, which is 0.1. Eta I is 0.1, means 10% of the total recombinations lead to generation of photon. If eta I equal to 0.5, it means 50% out of all the recombinations, 50% will lead to the generation of photons, while 50% do not. They are non-radiative recombinations. I have put some numbers here. So, it is interesting therefore to see what is eta I for these materials. So, you can take, let us take gallium arsenide first, okay, gallium arsenide. So, eta I is equal to 1 over tau R divided by 1 over tau R plus 1 over. So, this is, so 1 over 100 nanosecond, all are nanosecond. So, I do not have to write. So, 1 over 100 plus 1 over 100. How much is this? Okay. So, x divided by 2x, whatever be 1 over 100, so 0.5. If you look at silicon, so silicon, for silicon eta I is equal to, we can, if you want, you can use this directly. See this, what is the expression? 1 over tau is equal to 1 over tau R. This is 10 millisecond. So, 10 millisecond is 10 to the power of minus 2 seconds plus 1 divided by 100 nanosecond, 10 power minus 7 here. So, this is equal to, this is a very large number, because 1 over 10 power minus 2 is, this is 10 power, oh sorry, 10 power 2 plus 10 power 7, which is approximately 10 power 7, because 10 power 2 is negligibly small, all right, and therefore, tau is equal to, approximately equal to 10 power minus 7, approximately equal to, because this number is, so 1 over tau is about 1 10 to the power of 7, and therefore, tau is approximately this. Therefore, tau R, so 10 power minus 7 divided by tau R. Tau R is 10 millisecond, so 10 power minus 2 is approximately equal to. The internal quantum efficiency for silicon is 10 power minus 5, which means out of 100,000 recombinations, one will generate photon, all the rest do not generate photon. Similarly, you can find out for gallium nitride here, this is 10 nanosecond, this is 0.1 nanosecond. I think this will come out to be 10 power minus 2, approximately 10 power minus 2. Check what you get for this. So, the efficiency is relatively lower here, but see that gallium arsenide. So, this is an indirect band gap material, this is a direct band gap material. In general, direct band gap materials have eta I in the range 0.2 to 0.9, and indirect band gap materials have generally very low internal quantum efficiency, 10 power minus 3, minus 4, minus 5, minus 6, very small numbers. What does this tell you? If we want to realize a source, we should choose a material which is direct band gap, which has a large eta I. Incidentally, gallium nitride is also a direct band gap material, but this does not have a large eta I, Therefore, whenever sources are made, this is a wide band gap semiconductor. When people make sources, like for the blue LED, it is indium gallium nitride which is used, the ternary compound indium gallium nitride. This has a eta I of approximately 0.3. This is very small, eta I of gallium nitride, but indium gallium nitride, the ternary compound, has a very large internal quantum efficiency. So, the first point is, when you choose a material, choose to realize sources. Now, we are discussing in this part only about sources. Eta I, the internal quantum efficiency, should be as large as possible, so that there are more radiative transitions, more radiative recombinations, which lead to the generation of photons. Let us discuss a little bit more about injection electroluminescence. So, radiative recombination lifetimes and non-radiative recombination lifetimes and internal quantum efficiency. Please put some numbers and be familiar with the numbers of tau r, tau nr, and how to calculate internal quantum efficiency. In practical devices, when we say injection, we talk in terms of current I. If I is the current, we want to relate this to the power generated. Now, we want to go to the device where what is the power generated. So far, we have been talking about recombinations, rate, and so many things. Now, we want to come to the device engineer's perspective. He passes a current I, wants to know what is the optical power generated and how much is available to him. So, if I is the current, let us consider a PN junction. We use PN because it is very easy to inject current. So, a forward biased PN junction current. There is a current I which flows through the diode. What is the power generated? R is equal to delta n into tau. What is R? Number of carriers recombination, that is number of recombinations per unit time per unit volume. This is R. Number of recombinations per unit time per unit volume. What is I? I is current. Current is charge per unit time, rate of change of, so charge per unit time. So, what is the number of carriers per unit time? So, number of carriers per unit time, carriers per unit time. Please see, rate of recombination. Why a current flows through this? Because carriers are recombining at the junction region. The rate of recombination here is equal to the rate of injection, because it is the recombinations which is responsible for current flowing. So, every one recombination here leads to injection of an electron and a hole. So, rate of recombination equal to rate of injection. This is the important point, rate of injection. Rate of recombination of carriers equal to rate of injection of carriers. So, let me add recombination of carriers. Please see, this is the basic definitions, injection of carriers. I is the rate at which charge flows. What is the number of carriers that will flow per second? So, rate of injection of carriers is equal to I divided by E. Charge of one carrier is E. So, I divided by E will give you rate of injection of carriers. This is equal to rate of recombination of carriers. What is the rate of recombination of carriers? R, but this is per unit volume. In the current there is no unit volume. So, R into V, where V is the volume. Please see the logic. If R is the rate of recombination, then R into V will give you rate of recombination in the volume, because R by definition is rate number of recombinations per unit time per unit volume. Therefore, R into V will be number of recombinations per unit time, which is rate of recombination. So, rate of recombination of carriers is equal to R into V. I by E is equal to R into V. What is R? So, I by E is equal to R is delta n into tau. So, delta n by tau into V. Every recombination. So, what is power? Please see, this is the, what is the, our interest is power generated, that is power generated, optical power. We are interested in optical power generated. Every recombination, radiative recombination, every radiative recombination will give us one photon generation. We are interested in power generation. If n is the number of photons generated per unit time, what is the power generated? N into h nu is the power generated. If n is the number of photons generated per unit time, n h nu is the power generated. Power generated. N is the number of photons. This n is number, please, I have also used earlier n for carrier concentration, but this n is number of photons. If you want, you can put NPH for the time being, because it will all disappear in a short while. Finally, what we will get is just optical power, how it is related to current. That is all the device engineer wants, but it has to be linked from the basics, because all these while we have been talking of carrier recombination, photon generation, radiative transitions, non-radiative transitions, which does not mean anything to a device engineer. So, NPH into h nu gives you the power generated. Number of photons is determined by radiative recombinations. Out of all the radiative recombinations, eta I times radiative recombination, eta I times R will give you, all right, R is the rate of recombination. So, R into V is the rate of recombinations. Out of this, eta I is the fractional this is rate of recombination, which means number of recombinations per unit time in the volume V. So, eta I into R into V is the number of photons generated. Number of photons generated, eta I, because out of all the recombinations, a fraction eta I will lead to generation of photons, eta I into R into V. This is the number of photon generated, multiplied by h nu will give me power. Ni RV into h nu is the power generated, optical power. R into V is equal to I by E. So, this is equal to P optical generated. So, RV is replaced by I to E. So, eta I into I by E into H. Eta I into I by E into H nu is the power, optical power generated, P optical. So, I have got the expression that P optical, I am right now writing, afterwards we will drop, P means we are dealing with optical power only. Just at this point I am writing P optical generated, therefore, is equal to eta I. Some things can be simplified here. H is constant, nu is C by lambda, and Hc by E is 1.24. Anyhow, let me keep it as it is, I by E. So, H nu by E into I. So, this is the optical power generated. If you know a material, the internal quantum efficiency of the material, like any material we calculated for silicon gallium arsenide. If you know what is the band gap, H nu is close to Eg. So, you know this, you know E, you know the current, because current is the one which you are passing. So, for a given current you can calculate what is the power generated. So, we are now coming to how much optical power is generated. At this point I am giving emphasis on generation, because it is only generation, you have not yet got output. We have to see what is the output power that we are going to get. So, with this expression I will stop here and continue in the next class. We will see there are different efficiencies which are defined, because all of the generated power does not come out. Therefore, we have to see an extraction efficiency. There is a parameter called extraction efficiency, and finally, there is a parameter called wall plug efficiency, which means if you are supplying so much of electrical power, what is the optical power that you are getting. So, P optical divided by P electrical is called the wall plug efficiency. Wall plug, because you take the electrical power from the wall plug. So, it is called wall plug efficiency. We will discuss this in the next class. Okay.